Welcome to the deep dive. Have you ever paused to truly wonder what keeps a website safe? Or perhaps more intriguingly, what makes it vulnerable? Today, we're plunging into the fascinating and at times maybe a little bit scary world of web security vulnerabilities. Our mission is to equip you with the essential knowledge, giving you a powerful shortcut to truly understand the hidden risks online and, more importantly, how the experts tackle them. We've been immersed in a really comprehensive source titled Web Security Vulnerabilities and Mitigation Strategies. And this isn't just some list, it's more like a detailed blueprint. It lays out these threats, the precise conditions under which they emerge, and most critically, thoroughly explained mitigation strategies. It really feels like getting a behind-the-scenes tour of the internet security frontline.
It really is.
Yeah.
And what's truly fascinating here is that even if you're not writing a single line of code yourself, grasping these vulnerabilities offers you profound insight into the digital landscape you navigate every single day, which raises an important question. What does it genuinely mean to place your trust in a website with your sensitive information? This deep dive, I think, will illuminate so many aha moments for you. Things like understanding why your bank insists on multi-factor authentication, or why certain security warnings pop up. It gives you a much richer context for your online interactions.
Absolutely. So let's kick things off with one of the most widespread and well-known vulnerabilities, cross-site scripting or XSS. I think a lot of people might have heard the term, but it's probably a lot more nuanced than just bad code.
Yeah.
Can you walk us through the core conditions that allow XSS to happen and maybe why it's so persistent?
Certainly. For cross-site scripting, the core conditions are actually deceptively simple. It really boils down to a fundamental lack of trust, or maybe misplaced trust. It happens when user input is taken and directly inserted back into the web page's HTML, JavaScript, or even CSS without being thoroughly cleaned and made safe first. Imagine a website building a sentence for you on the fly, using your words, but forgetting to check if those words are actually, secret commands.
Okay.
So if there's poor input validation, meaning not checking what a user types in carefully enough, combined with a failure in output encoding, which is transforming that data into a safe format before displaying it, you've got a recipe for XSS. And this is particularly problematic with dynamic content, where parts of a page are generated in real time based on user input if secure templating or escaping mechanisms aren't rigidly applied.
Right. And I was surprised to learn there isn't just one type of XSS, which I guess really highlights its versatility for attackers. Could you elaborate on these different versions, how they play out?
Indeed, there are three primary types, each with its own sort of flavor of attack. First, we have stored XSS. This is arguably the most dangerous because the malicious script is actually saved on the server itself, often hidden away in a database.
Like in a comment section.
Exactly. Think of it like a malicious comment on a popular blog. Once it's posted, every user who views that comment later unknowingly loads and executes the attacker's script right there in their browser. The attack persists because the server is literally storing the malicious payload.
Got it.
Then there's reflected XSS. This type isn't stored on the server. Instead, the malicious script is bounced back, or reflected, to the user via an HTTP request. This is super common in phishing links. An attacker crafts a URL containing their malicious script, maybe embedded in a search query parameter or something.
Okay.
When you click that link, the vulnerable website simply echoes that malicious script back to your browser, which then executes it. It's more of a one-off attack for each click, but still highly effective for targeted phishing. And finally, there's DOM-based XSS. This one is a bit different because the malicious script is processed and executed entirely on the client side within your browser's document object model, or DOM. The vulnerability doesn't necessarily involve the server reflecting or storing the code. Instead, vulnerable client-side JavaScript itself processes user input unsafely.
Ah, so it's all happening in the browser.
Precisely. It causes the malicious payload to execute right there, often without ever directly interacting with the server's database or reflection logic in the traditional sense. Now, to combat XSS, the mitigations are multi-layered and absolutely crucial. First, and paramount, is to validate all user inputs against strict allow lists.
Allow list, not block list.
Yes, exactly. Don't just try to block known bad things because you'll inevitably miss something. Instead, define precisely what good input looks like only allowing numbers where numbers are expected and reject absolutely anything else. Second, apply context-aware output encoding.
Context aware.
Yeah, meaning how you encode depends on where the data is going. If you're putting user data into an HTML context, you must transform characters like up-based, and so they're seen as literal characters, not HTML tags.
Huh.
But if user data goes into a JavaScript context, it requires specific JavaScript escaping to prevent code execution there. Different contexts need different handling.
Makes sense.
Beyond that, always use secure templating engines. Things like Jinja 2, especially with its auto-escaping feature enabled by default. This automatically cleans potentially dangerous input when rendering pages. A truly powerful mitigation is implementing a content security policy, or CSP.
Right, CSP, you mentioned that. What does it do again?
Think of CSP as a strict bouncer at the club of your website. It tells the browser exactly which external sources, like script files or images or fonts, are allowed in. If a script tries to load from an unapproved place, the browser just says no, blocks it flat out.
Very useful.
And importantly, avoid using functions like inner HTML or, heaven forbid, evil in JavaScript for dynamic content generation. These functions literally execute any code you give them.
So it's like handing the keys over.
Pretty much, yeah. It's like giving an attacker a direct microphone to your browser's security system. Finally, for cookies, which often carry session information, use the HTTP-only flag.
HTTP only?
Yep. This flag basically tells the browser, hey, this cookie is super private. Even other scripts running on this page can't directly read it. This prevents attackers from easily snatching your session key via XSS. Also, the secure flag ensures cookies are only sent over HTTPS encrypted connections. And optionally, the same site flag can prevent cross-site requests from including cookies, which actually leads us perfectly into our next topic.
Okay, so the core insight here seems to be that when a website trusts your input too much or doesn't properly sanitize what it's showing back to you, it can literally turn its own pages against its users. It's like a classic case of a website becoming an unwitting accomplice in an attack.
That's a great way to put it.
Now, here's where it gets really interesting with our next vulnerability. Cross-site request forgery, or CSRF. Imagine you're logged into your bank, right? And then you click a seemingly innocent link somewhere else, maybe an email or on some forum post. What could possibly happen?
CSRF. Yeah, this one's sneaky. With CSRF, the main conditions are that your user session cookies are automatically sent by your browser with requests, and the target website doesn't have any additional verification like a special token to confirm you intended that request.
So the browser just sends the cookie.
Right. If you're logged into your bank and a malicious site tricks your browser into sending a request to your bank server, say, a request to transfer money or change your password, your browser automatically includes your valid session cookie with that request. The bank server sees that valid cookie and thinks, oh, this must be a legitimate request from the logged-in user. It has no idea the request was triggered by a different malicious site.
Wow, so the website acts on the attacker's behalf without knowing it.
Exactly. It's like a website unknowingly performing an action for an attacker, simply because your browser brought the secret key, your session cookie, along for the ride.
So how do you stop that?
The primary defense is using CSRF tokens. You include a unique, unpredictable token in every form or request that changes something on the server, any state-changing action. The server generates this token, embeds it in the page, and then when the form is submitted, it checks if the submitted token matches the one it expected for that session.
Like a secret handshake.
Precisely. If the token doesn't match or is missing, the request is rejected. It proves the request originated from the legitimate site itself, not some other site. Another strong defense, which we touched on, is using same-site cookies, especially with stricter lags attributes.
Right, the cookie flags.
Yeah. This attribute tells the browser, hey, don't send this cookie, along with requests that originate from other websites. This effectively blocks many cross-site requests that CSRF relies on. And of course, for really critical actions, simply requiring the user to re-authenticate, enter their password again, or use a second factor can also stop these attacks cold. Checking referrer or origin headers is sometimes done, but it's considered less reliable than tokens or same-site cookies.
Got it. So the core insight for CSRF is really about the browser's implicit trust, maybe? Your browser's trying to be helpful by automatically sending your session cookies, but without those extra checks, like tokens or same site, that helpfulness can be exploited to force you into actions you never intended.
Spot on.
Okay, so what does this all mean for the actual data stored in databases? That brings us to SQL injection, doesn't it? A classic, you could say, and still a really potent threat that directly targets the heart of an application's data.
Oh, absolutely. SQL injection, or SQL. It occurs when user inputs are directly concatenated or sort of glued together into SQL queries. Basically, if a developer builds an SQL query by just sticking user-provided text right into their database command. For example, directly placing a username from a login form into a select statement.
Without cleaning it first.
Exactly. If they do that and they don't use something called parameterized statements, an attacker can manipulate the database. They can insert their own SQL commands into what you thought was just a harmless input field, like a username or a search box. Things like drop table to delete data or select from users to dump sensitive information.
So they're literally rewriting the database command.
Yes. Think of SQL injection as an attacker talking directly to the website's brain, that database. If the website isn't listening carefully and sanitizing those inputs, separating commands from data, it might just do whatever the hacker tells it to.
That sounds bad. How do you prevent that?
The most critical mitigation, without a doubt, is using parameterized queries or prepared statements.
Parameterized queries. How does that work?
Instead of directly injecting user input into the SQL string, you pass the input as a separate, distinct parameter to the query. The database engine then handles it safely. It understands that the userid, for instance, is a value to be searched for, not part of the SQL command itself. So for example, in Python, with a typical database library, instead of building the string yourself, you'd use something like cursor.execute. Select from users where it is %userid.
Okay. The percents is a placeholder.
Exactly. The database knows that % is a placeholder for data, not a place for new instructions. It handles the quoting and escaping safely behind the scenes. Also, using object relational mappers, or ORMs, like Squalchemy or Django's ORM, is a huge help. They abstract away the raw SQL execution and often build in these protections by default, making it much harder for developers to make this kind of mistake.
Good practice then.
Definitely. And of course, always validate and sanitize inputs rigorously. Reject anything invalid or unexpected based on what you expect that field to contain. Employ the principle of least privilege for database accounts. The web application's database user should only have the absolute minimum permissions needed to do its job, not full admin rights. And finally, web application firewalls, or WFs, can sometimes help detect and block common malicious SQL query patterns before they even reach your application or database. It's a defense-in-depth approach. Right. So the key takeaway for SQL injection, it's all about how a website talks to its database. If user input isn't clearly separated from database commands, an attacker can literally rewrite the conversation, leading to data theft, modification, or even complete database destruction.
Precisely. It's about keeping data and instructions separate.
Okay, now let's talk about server-side template injection, or SSTI. This one often flies under the radar, maybe, compared to SQL or XSS, but it sounds particularly nasty because the malicious code gets executed on the server side, not just in my browser. That's absolutely right. SSTI can be very severe. The conditions for it are when user inputs are directly embedded into server-side templates. You see, many web applications use templating engines, things like Jinja 2 in Python, Timeleaf in Java, Handlebars in Node.js, to generate dynamic HTML pages.
Right, to put the data into the web page structure.
Exactly.
Yeah.
Now, if these engines are configured insecurely, or if user input is passed into them without proper sanitization, and if those templating engines support the execution of arbitrary code, which many do for legitimate complex template logic,
Then you have a problem.
you have a big problem. An attacker could potentially inject template syntax that allows them to execute commands on your server, access sensitive files, probe the internal network, or even escalate privileges. It's a direct hit on the website's core functionality.
So how do you mitigate that? Seems tricky.
The simplest rule is to avoid including raw user input directly in templates, if at all possible. Find other ways to achieve the desired result. When you do need to use template engines with user input, ensure they are configured with restricted execution capabilities. For Jinja 2, for example, you can use strict configurations or sandboxed environments, or at the very least, apply explicit escape functions, like Jinja 2's markup.escape, or similar functions in other engines, to all untrusted data before it hits the template. And again, rigorously validate user inputs to prevent anything that looks like template syntax from being passed through in the first place. Consistently using secure web frameworks and libraries that have these built-in protections and follow best practices makes it much harder for developers to inadvertently introduce these flaws.
Okay. So the core insight here is that SSTI takes the idea of code injection, which we usually associate with browsers and XSS, and moves it directly onto the server itself. If a website's templating system isn't carefully controlled and locked down, it can become a backdoor for attackers to run their own code on the very machine hosting the application.
Exactly. Server-side execution is the key difference and danger here.
Next up is HTTP request smuggling. This sounds a bit more, nuanced, more under the hood. It exploits how different parts of a web server infrastructure handle requests.
Yeah, this is a more sophisticated and often tricky one to detect and understand. Request smuggling happens when different back-end systems, typically a front-end proxy server like a load balancer or a CDN, and a back-end application server, interpret the same malformed HTTP request differently.
Differently how?
It usually stems from a discrepancy in how they handle two specific HTTP headers. The content length header, which specifies the length of the message body in bytes, and the transfer encoding header, often set to chunked, which indicates the message body is sent in chunks of varying sizes. One server in the chain, say the front-end proxy, might prioritize content length, while the back-end server might prioritize transfer encoding, chunked. If an attacker crafts a request that has both headers and they conflict, one server might think the request ends at a certain point, while the other thinks it continues.
So part of the request gets left over.
Exactly. Parts of that first legitimate-looking request get left dangling in the connection buffer, and they're then mistakenly prepended to the next legitimate request that comes down that same connection, often from a different user. This allows an attacker to smuggle a harmful second request past security controls on the front-end proxy because the proxy only saw the first seemingly harmless part.
Wow, that's subtle. How do you defend against that?
Mitigations generally involve using modern secure web servers and proxy servers that strictly adhere to HTTP parsing rules according to the latest RFC standards. They should reject ambiguous requests with conflicting headers. Ensuring consistent validation and interpretation of headers across both front-end and back-end servers is crucial. They need to agree on where one request ends and the next begins. If transfer encoding chunked isn't strictly required for your application's functionality, disabling it on the front end or ensuring it's handled correctly throughout the chain can remove a common vector for this attack. And regular security testing with specialized tools like Burp Suite Scanner is often necessary. Security professionals use these tools specifically to probe for these kinds of desynchronization vulnerabilities, as they are hard to spot with conventional methods.
Right. So the core insight for HTTP request smuggling is that it's a subtle attack exploiting inconsistencies in how web servers handle the basic structure of requests. It's like finding a secret side door because the front and back of the house don't quite agree on where the main entrance actually ends. Allows attackers to sneak malicious commands past defenses that aren't perfectly in sync.
That's a good analogy, yes. It's all about that desynchronization.
Let's move on to directory traversal, which focuses on unauthorized file access. It sounds kind of simple, maybe, but the implications can be quite severe, I imagine.
Oh, definitely. Directory traversal, sometimes called path traversal, occurs when user inputs are used to construct or access file paths without sufficient validation. Essentially, if an attacker can feed something like buck, which in file paths means go up one directory level into an input field that's supposed to just take a file name or maybe a relative path.
Like for viewing an image file.
It's exactly. If the application takes that input, say, at set of pass WD, and uses it to build a file path without properly cleaning it or restricting the final path, the attacker might be able to navigate out of the intended webroot directory. They could potentially access sensitive files elsewhere on the server configuration files, source code, system password files, you name it. It's literally about an attacker trying to climb out of the allowed web directory sandbox.
How do you prevent that climbing out?
The key mitigations are, first, to validate and sanitize any user input used in file paths meticulously. Use an allowist approach if possible, only permitting known good file names or patterns. Critically, use secure file system APIs provided by the operating system or language standard library. For instance, functions like Python's os.path.abspath or Java's file.getCanonicalPath can help resolve paths securely.
How they help?
They normalize the path first, resolving all the components, and then you can check if the resulting absolute path still starts with your allowed base directory. If it doesn't, you reject the request. Also, you should configure the web server and application to restrict file access to only very specific directories needed for the application, essentially creating a jail or CRUT environment for user-accessible files if possible. And finally, always apply the principle of least privilege for the web server's file system permissions. The user account the web server runs as should only have read access, or write, if absolutely necessary, to the specific directories it needs, not the entire file system.
Okay, so the core insight for directory traversal is it's an attack on file access control. If a website lets user input dictate file paths without really strict checks and path normalization, an attacker can potentially break out of designated web directories and gain unauthorized access to critical system files.
That's it, exactly. Control the paths.
Open redirect is next. You hear about this one a lot, often used as a stepping stone in phishing attacks, right? Like a seemingly trustworthy signpost that actually points you somewhere dangerous.
Precisely. Open redirect vulnerabilities arise when an application takes a URL provided by a user, often in a query parameter like .redirecto some-other-site.com, and automatically redirects the user's browser to that URL without properly validating if that URL is safe or allowed.
So why is that dangerous?
Because an attacker can craft a link that looks legitimate. It starts with a trusted domain, say your-bank.com/login.redirecto evil-phishing-site.com. The user might see the your-bank.com part, think it's safe, click it. The bank site might briefly load, then instantly redirect them to evil-phishing-site.com. This can trick users into giving up credentials on a fake login page because the initial link looked trustworthy. The legitimate site becomes a brief, trusted stepping stone to a malicious one. It leverages the trust users have in the initial domain.
Ah, okay. How do you stop websites from being abused like that?
The best way is to never allow redirection to arbitrary URLs provided by users. Instead, restrict all redirects to an allow list of known, trusted, predefined URLs or paths within your own site or sister sites. If you absolutely must allow redirects based on user input, perhaps use an internal identifier or code that maps to a known, safe destination URL on the server side, rather than accepting the full URL directly. Always encode and sanitize any user-provided URL components before using them, just in case. And critically, avoid just blindly reflecting user input in the location header for redirects. If a redirect to an external site is absolutely necessary and unavoidable, it's often best practice to show an intermediate page first.
A warning page.
Exactly, a page that says, "You are now leaving example.com. Click here to continue to external-site.com." This makes it very clear to the user they are navigating away from the trusted domain.
Got it. So the core insight for Open Redirect is that trust can be manipulated. If a website doesn't rigorously check where it's sending users based on input, it can be abused to make a phishing link seem legitimate, guiding unsuspecting users directly into an attacker's trap by using the site's own reputation against it.
Well put. It's a vector for social engineering.
Authentication bypass sounds, well, pretty self-explanatory and incredibly serious. It could completely undermine all your other security layers, right? It's like the digital equivalent of someone just walking straight into your house without needing a key.
It is extremely serious, yes. Authentication bypass conditions occur due to flaws in the site's authentication logic itself. This could be things like weak or guessable session tokens, flaws in password reset mechanisms, or maybe allowing direct access to privileged endpoints or pages without properly checking if the user is actually authenticated and authorized.
So someone could just access admin functions.
Potentially, yes. Maybe they can simply change a user ID parameter in a URL, or manipulate a cookie value, or find a page that was supposed to be protected, but developers forgot to add the authentication check, and suddenly they have administrative privileges or can access another user's account without ever actually logging in correctly.
Yikes. How do you prevent that? Seems fundamental.
It is fundamental. The mitigations involve using strong, industry-standard authentication methods. Things like OAuth 2.0, OpenID Connect for federated identity, or robust, well-vetted, session-based authentication libraries that generate cryptographically strong, unpredictable session tokens. Crucially, you must enforce authorization checks, usually role-based access control, RBAC, everywhere. Every single request for a privileged function or sensitive data must be checked server-side to ensure the authenticated user has the necessary role or permission. You can't rely on just hiding links in the UI.
Assume attackers will find the direct URLs.
Always assume that, yes. And implement secure session handling practices. Always regenerate session IDs upon successful login or any change in privilege level, like becoming an admin, to prevent session fixation attacks, which we'll probably get to. And make absolutely sure your session cookies have the HTTP-only, secure, and same-site attributes set correctly to protect them from various attacks like XSS and CSRF trying to steal or misuse them.
Okay, so the ultimate goal for an attacker with authentication bypass is getting in without the key, or maybe becoming someone they're not supposed to be. If a website's main gates aren't perfectly guarded and checked every time, all the other security measures inside can quickly become meaningless.
That's the crux of it. Authentication is the front door.
Now, related to that, let's talk about insecure direct object references, or IDOR. This one sounds like it's about predictable IDs and how attackers can exploit them.
Exactly. IDOR happens when an application grants access to an object or a piece of data based solely on an identifier for that object provided by the user without performing any additional authorization checks to see if that specific user is actually allowed to access that specific object.
Can you get an example?
Sure. Imagine a URL like https.example.com/order.ordered123. If you, as a logged-in user, can simply change that order in the URL to 124 and suddenly see someone else's order details without the application checking, hey, does the current user actually own order 124, then that's an IDOR vulnerability. The application directly exposes the object's real identifier, like a database primary key, and just trust that if the user provides it, they must be allowed to access it.
So how do you fix that? Seems like a common pattern.
It is common, and the fix is crucial. You must enforce rigorous authorization checks for all sensitive actions or resource accesses. This means every time a user tries to access or modify data identified by an ID, the application needs to verify. Is the currently authenticated user allowed to perform this action on this specific object? Usually this involves checking ownership or permissions associated with the object against the user's session.
Don't just trust the ID they provide.
Never just trust the ID. Another good practice is to avoid exposing direct database keys or sequential guessable identifiers directly to the user in URLs or forms. Instead, use indirect references. Map those internal object IDs to, say, long, random, unguessable strings like UIDs or per-user references that are only meaningful within that user session. This makes it much harder for an attacker to simply guess or iterate through IDs to find other people's data. It masks the true ID.
Okay, so the core insight for IDOR is about predictability and missing checks. When a website exposes its internal object identifiers directly and doesn't double-check authorization for that specific object, an attacker can often just guess their way to other users' private data or resources. It's like finding a secret shortcut that bypasses the necessary permission gates.
Precisely. Authorization must be object level.
Moving on to file upload vulnerabilities. You know, many people probably think of file uploads as just sharing pictures or documents, but the risks can go way beyond that, can't they?
Absolutely. This is a classic and often very dangerous point of entry for attackers if not handled carefully. File upload vulnerabilities occur if user-uploaded files can somehow be executed by the server, or if they overwrite critical system files, or if they contain malware that affects other users who download them. The main risk is usually that an attacker uploads a malicious script file, like a PHP web shell, or an ASPX file disguised as something innocent, like an image, shell.jpg.
But it's actually code.
Right. If the server doesn't properly validate the file's actual content and type, and if it stores that file in a directory where the web server might try to execute scripts, like the main web root, then the attacker might be able to browse to upload shell.jpg and have the server execute their code, giving them remote control. That's how many web shells, essentially backdoors, are planted.
Okay, that's bad. How do you stop that?
Several layers are needed. First, validate uploaded files rigorously. Don't just trust the file extension, .gpg.gng, because that's trivially easy to fake. You need to check the file's MIME type, as reported by the browser, though even that can be spoofed. And more importantly, inspect the actual file content. You can do this by checking magic bytes.
Magic bytes.
Yeah, these are unique sequences of bytes in the very beginning of a file that identify its true format, like FFD8FF for JPEG. You compare these against an allow list of permitted file types. Second, and critically, store uploaded files in a directory outside the web root, or at least in a directory where the web server is explicitly configured not to execute any scripts. Treat uploaded files as static data, not code. Third, it's generally a good idea to rename uploaded files on the server to something random or based on a hash, rather than using the user-supplied file name directly. This prevents potential overwriting of existing files and can also mitigate some path traversal issues if the file name itself contains things like DE. And finally, consider using server-side virus scanning on all uploaded files as an additional layer of defense, especially if users can download files uploaded by others.
Right. So the core insight here is that if a website lets you upload files without thoroughly checking what they really are based on content and without storing them safely away from executable locations, it can be like inviting a Trojan horse directly onto their server. What looks like a simple image could actually be a program taking over the system.
Exactly. Treat all uploads as potentially hostile until proven otherwise.
Session fixation sounds interesting.
Yeah.
It's about how an attacker can somehow fix your session before you even log in and then potentially hijack it later. How does that work?
Yeah, session fixation is a clever attack on the session lifecycle. It happens when an application allows session identifiers to be set before authentication, perhaps via a query parameter in a link, and then fails to regenerate a new session ID after the user successfully logs in.
So the ID stays the same before and after login.
Potentially, yes. An attacker could trick a user into clicking a link like https://example.com.session. Attacker knows TISID. The user's browser now has this preset session ID. Then the user proceeds to log in on that site. If the application doesn't create a fresh new session ID upon successful login, that existing ID, attacker knows this, it simply gets elevated to an authenticated state. Since the attacker already knows that session ID, they can now potentially use it in their own browser to hijack the user's authenticated session. It's like an attacker giving you a preset tainted key, and then when you use it to unlock your account, they still have a copy of that key.
Ah, I see. So the fix is about changing the locks after login.
Essentially, yes. The primary mitigation is to always regenerate the session ID immediately upon any successful authentication or change in privilege level. Discard the old pre-login session ID entirely and issue a brand new cryptographically random one for the authenticated session. Also, ensure you're using secure session tokens to begin with, make them long, random, and unpredictable. And consistent with what we've discussed for other vulnerabilities that target sessions, always set session cookies with the HTTP-only, secure, and same-site attributes to provide layered protection against theft or misuse of those session IDs.
Okay, so the core insight for session fixation is that an attacker can potentially taint your connection or session with a website before you even log in. If the website isn't careful about refreshing that session identifier and issuing a completely new one after you prove who you are, the attacker can then use their prior knowledge of that initial ID to impersonate you.
That's it. Always generate a fresh session ID post-login. Our next vulnerability, security misconfiguration, sounds like it highlights that sometimes security failures aren't about clever hacks, but maybe just simple oversight, about what isn't done correctly.
That's absolutely right. Security misconfiguration is consistently one of the top vulnerabilities found by organizations like OWASP, precisely because it's so common and often involves basic errors rather than complex exploits. It happens when default configurations are left unchanged, or unnecessary features or services are left enabled, or error messages are too verbose and reveal sensitive internal information.
Like leaving the default admin password.
Exactly like that. Or leaving debugging features enabled in production, or having directory listings turned on, revealing file structures, or running outdated software versions with known vulnerabilities, or having overly permissive firewall rules or cloud security group settings. Often the biggest security risks aren't these super complex zero-day exploits, but simply leaving the digital backdoor unlocked or giving away too much information about the internal setup by accident through poorly configured error handling.
So how do you systematically address misconfiguration?
It requires diligence and process. First, you need to thoroughly harden all application, framework, web server, database, and operating system configurations. This means actively disabling default accounts immediately, changing all default passwords, removing any unnecessary services, features, and open network ports. Follow security hardening guides for your specific technologies. Second, configure error handling carefully. Mask detailed technical error messages in production environments. Show users generic, uninformative error pages instead of stack traces or database error details that could leak internal system information valuable to an attacker. Log the detailed errors securely on the server side for developers to diagnose. And crucially, automate configuration reviews and security checks as much as possible. Use security scanning tools like OSP's AAP, vulnerability scanners, and cloud security posture management CSPM tools to systematically and regularly check for common misconfigurations across your infrastructure. Manual checks are prone to errors and omissions.
Right. So the core insight for security misconfiguration is that security isn't just about patching known flaws in code. It's also about diligent setup, maintenance, and hardening of the entire environment. Leaving default settings active or unnecessary features enabled can expose sensitive information and create easy, low-hanging fruit entry points for attackers.
It's foundational security hygiene, really.
Let's discuss clickjacking. This one sounds like a clever form of visual deception, maybe. It's not about stealing your data directly, perhaps, but tricking you into doing something you don't intend to.
That's a perfect description. Clickjacking, sometimes called UI redressing, occurs when an attacker uses multiple transparent or opaque layers, usually involving iframes, to trick a user into clicking on a button or link on a different website, the one they think they are interacting with.
How does that work visually?
An attacker creates their own malicious web page. On that page, they embed your legitimate website, say your bank's transfer funds page, inside an invisible iframe. They then carefully position this invisible iframe so that the Confirm Transfer button on your bank's page lines up perfectly underneath something seemingly harmless on their own page, like a Play Video button or Win a Prize link. The user sees the attacker's page and tends to click the Play Video button, but their click actually goes through the invisible layer and registers on the Confirm Transfer button within the hidden iframe of the bank's site.
Wow. so you perform an action without even realizing it.
Exactly. It's about hijacking your click, tricking your eye and your mouse pointer. Maybe you click on one thing while actually activating something completely different and potentially dangerous on a hidden, legitimate site where you might already be logged in.
How do websites prevent themselves from being framed like this?
The primary defense is an HTTP response header called XFrame options. Setting this header to DNY tells the browser, do not allow this page to be displayed in any frame or iframe, period. Setting it to SAM origin is slightly less strict. It allows the page to be framed, but only by pages from the exact same domain origin as the page itself. This prevents external sites from framing it. There's also a more modern and flexible approach using a content security policy, CSP directive, called frame ancestors. This allows you to specify exactly which origins are allowed to embed your page in a frame, offering more granular control than XFrame options. Using one or both of these is crucial.
Okay, so the core insight for clickjacking is that deception isn't just about fake emails. It can be purely visual right there on your screen. If a website doesn't explicitly tell browsers, don't let other sites embed me, attackers can create these invisible overlays that trick you into clicking sensitive functions without your knowledge by manipulating what you see versus what you click.
Exactly. Controlling where your content can be framed is key.
Next up is broken access control. You mentioned this earlier, and it sounds like a really broad category covering various kinds of privilege issues, ranging from simple oversights to maybe complex logical flaws in how permissions work.
It is a very broad and extremely common category, yes.
Yeah.
Broken access control essentially means that restrictions on what authenticated users are allowed to do are not properly enforced. This happens when privilege actions or access to data aren't correctly validated on the server side for every single request. It allows users to potentially access functions or data that they shouldn't be able to, based on their role or permissions.
Well, like a regular user getting into an admin panel.
That's a classic example. Or maybe changing .userid123 to .userid124 in a URL lets you edit someone else's profile, similar to IDOR but focused on the action privilege. Or perhaps bypassing an access check that was only implemented in client-side JavaScript but not reinforced on the server. Or maybe forcing browsing to internal admin URLs that weren't meant to be public. It's like a junior employee being able to easily walk into the CEO's office, access sensitive files, or even change company policies simply because the lock on the door wasn't truly secure or checked properly every time.
How do you build robust access control then?
The key is to implement centralized access control checks, preferably in a single, well-tested component or middleware that handles all requests. Every request that seeks to access data or perform an action should pass through this robust permission check on the server, verifying the user's session and their specific permissions before executing the requested action. Enforce the principle of least privilege using models like role-based access control, RBAC, or potentially attribute-based access controls, ABAC, to precisely define what each user role or combination of attributes is allowed to do. Deny access by default. And, crucially, you need to regularly test for access control vulnerabilities. This includes trying to access functions as different roles, manipulating IDs and parameters, trying to force browse to internal pages, essentially, penetration testing specifically focused on breaking your own access controls to ensure they are holding up against determined attackers. Don't just rely on hiding links or buttons in the UI.
Right. So the core insight for broken access control is really about boundaries and enforcement. When a website doesn't consistently and strictly enforce who can do what on the server side for every single request, users or attackers can often find ways to bypass those controls, access features or data they shouldn't, turning a standard user into an accidental administrator, which is, of course, an attacker's dream.
Precisely. Enforcement must be pervasive and server-side.
Okay, finally, let's discuss XML External Entities, or XXE. This sounds a bit more specific, focusing on vulnerabilities and how applications process XML data, potentially exposing internal server details.
Yes, XXE is a vulnerability related to XML parsing. It arises when an application processes XML input from an untrusted source, and the XML parser is configured to process something called external entities.
External entities, what are those?
The XML documents have a feature where you can define custom entities that act like shortcuts or variables within the document. Some entities can be defined as external, meaning their value is fetched from an external resource, like a file path on the local server or a URL. Now, if an application accepts XML input, say in an API request or a file upload, and its XML parser is configured to process these external entities, which some older or poorly configured parsers do by default, an attacker can craft malicious XML input.
To do what?
To make the server retrieve sensitive local files. For example, they could define an entity, entity-sensitive file system file.eccpasswd, and then reference a sensitive file somewhere in the XML data. When the server parses this, it might try to read SQL as found from its own file system and embed its contents into the parsed XML result, potentially revealing it back to the attacker in an error message or the application's response. It can also be used for server-side request forgery, SSRF, by defining entities that point to internal network URLs, or even for denial of service attacks by forcing the server to fetch huge files or recursively defined entities, a million laughs attack.
Okay, so how do you prevent XXE? It seems like you should just turn that feature off.
That's exactly the primary mitigation. Disable external entity resolution in your XML parsers. Almost all modern secure XML parsing libraries provide a configuration option to explicitly disable the processing of DDDs, document type definitions, and external entities. This should be the default setting when parsing any untrusted XML input. Use modern, well-maintained XML processing libraries that have secure default configurations. For instance, in Python, the standard XML libraries can be vulnerable if not configured carefully, which is why libraries like diffused XML exist. They wrap the standard libraries with safe defaults, disabling external entities and other dangerous features automatically. And as always, validate and sanitize XML inputs as much as possible before parsing, although disabling the dangerous parser features is the most reliable defense against XXE itself.
Got it. So the core insight for XXE is that even standard structured data formats like XML can harbor hidden dangers if not processed carefully. If a website's XML parser isn't properly configured to ignore these external entity features, attackers can potentially abuse them to force the server to reveal sensitive internal files, probe the internal network, or participate in other attacks, all triggered by specially crafted XML input.
Correct. Secure parsing configuration is vital.
Wow, that was a truly deep dive into the complex world of web security vulnerabilities. I mean, from malicious scripts hiding in your browser to these sneaky manipulations of server logic, even just leaving default settings active. It's clear there's an immense amount to consider to keep websites truly secure.
It really is a huge landscape. And if we connect this back to the bigger picture for everyone listening, understanding these specific vulnerabilities, even at a high level, gives you a much richer context for why certain security practices are so crucial for the apps and websites you use every single day. Whether you're logging into your bank, using social media, or shopping online, knowing about XSS helps explain why sites are careful about user comments. Knowing about CSRF explains why some actions need re-authentication. Knowing about SQL explains why input validation is so critical.
Right, it demystifies things.
Exactly. It explains why developers use specific frameworks, why your browser might warn you about insecure connections or mixed content, and why software updates patching these very flaws are so incredibly important. Knowing these specific threats helps you understand the why behind all the digital precautions we encounter. And maybe this raises a final important question for you to think about. In a world where so much of our lives are online, how much of the security we generally experience day to day is actually due to perfect, flawless code, which is probably quite rare, versus the constant, diligent, ongoing work of security professionals identifying and mitigating these very specific vulnerabilities as they emerge and evolve? It's really an ongoing battle, isn't it? A continuous process of defense, detection, and adaptation. And maybe knowing a bit more about what's happening behind the scenes shapes how you view your own digital experience and safety.
That's a great point to ponder. We certainly hope this deep dive encourages your continued curiosity and helps you appreciate the immense, often invisible effort that goes into securing our digital lives. Stay curious and stay informed.